Okay, so everybody fine? So let's start. Conrado, the floor is yours. Please go ahead.
Thank you. So good morning, everyone. Good afternoon, Maximilien. I'm Conrado, and today I'll be defending my master's dissertation, which is entitled Analysis of Firing Rate and Correlation of Spike Trains from a Brain Network Model with Cluster. And I like to begin by setting the scene. Studying neurons in isolation has provided us with much important knowledge about brain cells. So we know that neurons communicate through action potentials, which are electrical signals. We know that these signals always travel from the dendrites to the axon terminals, and this phenomenon is called dynamic polarization. We know that a neuron, even though it doesn't receive any contribution from other neurons, it still can fire by spontaneous activity. And we also know that the synapses, that is the places where a neuron connects to another neuron, can be both excitatory or inhibitory, depending solely on the neurotransmitters presented in the presynaptic axon terminal. But although we have all this information, it's not enough to understand how the brain do such complex tasks as, for example, thinking. To understand that, we need to study the brain as the complex network it truly is. So if we had the connections of the brain, and we also had the communities of the brain, so the brain is subdivided into communities that have denser connections within themselves than between communities. If we had this information, we could try to predict the dynamical system of the brains and predict whether a neuron will fire or not. But sadly, we don't have these connections. And it's even worse because we don't have the community membership of each neuron. What we do have is we have some brain exams that can measure neuronal activity, and this activity can be converted into time series of spike trains that tells us whether a neuron fires or not at each given time step. With this time series, we can do some things, for example, compute the average firing rate of a single neuron, or compute the covariance or correlation of a pair of neurons firing. Okay, and with this statistics, we can try to recover the community membership of each neuron, and many prior works attempt to do so. What we do here in this dissertation is to provide analytical expressions for mean firing rate and for covariance of pairs of neurons in both a fixed graph environment and in a random graph environment that can guide us to really reconstruct the community membership of each neuron. Using these statistics, here we give formal proofs that these things are possible. The first thing we need is to model the neuronal activity. So what we do have is a set of n neurons that are partitioned into two disjoint communities, C1 and C2. And we'll write that I is similar to J if they belong to the same community, and that I is dissimilar from J otherwise. So to model the connections of the neurons in the brain, we have a direct adjacent matrix theta that has values equal to 1 if I has a direct edge to J and 0 otherwise. So note here that this is not symmetric. We can have an edge from I to J, and having that J has not a connection to I. We also have a edge class matrix that tells us if that edge is excitatory or inhibitory. It has a value of +1 if the edge I to J is excitatory, and -1 if the edge from I to J is inhibitory. And to summarize all this information, we have an interaction graph G that tells us which are the communities, tells us the adjacent matrix, and the class of each edge. Okay, so now let's take a look at this example here. We have two communities, one purple and another one green. The blue edges are excitatory and the red edges are inhibitory. So we could ask ourselves, what is the average firing rate of neuron 5 given this network? Or what is the covariance between the firings of neurons 1 and 6 in this network? And that's what we try to answer here in this dissertation. To do so, we need to model the neuronal activity. So we model them through random variables x, I, t, have a value equal to 1 if I fires at time t and 0 otherwise. And to summarize the information about the whole system at a given time t, we have this vector xt here. But how does this system evolves in time? It evolves as a discrete time Markov chain with this transition probability here that is the product of the independent probability of each neuron firing considering the previous time step. Considering that the system has this state x at the previous time. Okay, so this term here is the probability that neuron I fires at the given the system previous state. And how do we model it? So this, as I said, this is the mathematical definition of this term. And we model it through this equation here, in which the first term reflects the spontaneous activity. So we can consider it as the baseline of firing probability, even though none of their neighbors contributes to its firing, it still has a probability of firing equals to lambda. The second term is sum over the neurons that are in the same community as I, and the third term is over the neurons that are in the different community. And so we have this weight here, me in, that's how we call it, me in over n and me out over n. That is the edge weight of these contributions. So consider that we have an edge from j to I, that this edge is excitatory, and that j has fire in the previous time step. Then the contribution to neuron I firing in the actual time step we have is increased by me in over n. And so if we have that same network, considering we have a firing probability, spontaneous firing probability of 0.25, me in is equal to 3 and me out is equal to 1. Consider that this circle neurons here have fired at the previous time step. What is the probability of neuron 2 firing? Well, note that we have 2 excitatory intercommunity edges pointing to 2, and we have inhibitory intercommunity edge pointing to 2. So the probability of neuron 2 firing given this previous state is given by 0.25 plus 3 over 9 times this sum here, plus 1 over 9 times this sum here. This sum here, as I said, we have 2 excitatory contributions, intercommunity contributions, so we put a 2 here. And here we have inhibitory edge, so minus 1. And we get this result, so the firing probability of neuron 2 is approximately 0.805. And to summarize all this information, and we can rewrite this equation in a simpler way, we use this interaction matrix A here that has the information about the weights of contribution, that has the adjacent matrix, the edge class type, edge class here, excitatory or inhibitory, and whether the neurons are in the same community or not. And so we can rewrite this probability in a matricial way using A transpose times X, which is the previous time system configuration. Okay, but as I said, this is the probability of neuron I firing, so it should be in the interval 0 to 1. And how do we guarantee that? We have some restrictions over the model parameters. So we relate the adjacent the interaction matrix A with lambda. And this is a sufficient condition to guarantee that indeed we have a probability for neuron I firing. So again, how do we answer these questions? What is the average firing rate of a neuron, or what is the covariance between the firings of 2 neurons? We'll need some definitions first. So we call firing mean the expected value of this random variable xit. And as xit is a Bernoulli random variable, has only values 1 or 0, this expected value is equal to the probability of neuron I at time t being equals to 1. Here we don't have the dependency of t on the left side of the equation, because we consider that the Markov chain has reached a stationary distribution. As this random variable is a Bernoulli, we can compute its firing variance by this equation here. So we have the firing mean times 1 minus the firing mean of that neuron. We'll also have to define 2 firing covariances here. The synchronous firing covariance, which we write as sigma 0, and that is the covariance between 2 neurons at the same time step. and the one-lagged firing covariance, which is the covariance of two neurons given one lagged time series. So J is at time t minus 1 and I is at time t, and write that as sigma 1. But why do we consider these two covariances? Intuitively, the first one reflects more common in neighbors. So if I and J have they are always firing together, or if they are inhibited together, probably they have much common neighbors that are contributing to both their probability firing. And the second one reflects more direct connections. So if I have every time J fires, I then fires in the next time step, this probably reflects a direct connection. So with these definitions, we can enunciate our first important result, which is this theorem here. They give us the firing mean for all neurons based solely on the model parameters. So here we have the interaction matrix and model parameter lambda. And with this theorem, we can compute the firing mean for all neurons. So let's take this example here. We consider that the spontaneous activity is equal to 0.25, and we have this interaction matrix here. Note that all edges are excitatory. So we can compute the firing mean, and we achieve this result here. Note that neurons 1 and 2 have no in contributions, so their firing probability cannot be changed, and thus its firing mean is equal to the spontaneous activity. On the other hand, 3 and 4 both receive excitatory contributions from 1 and 2, and so their firing mean is increased. To our next result, we will need to define two operations, and I'll do that through an example here. Consider we have a vector W. Diag of W is the matrix having this vector as its main diagonal, and all the off main diagonal values equals to 0. And consider we have a matrix M. D of M is a transformation that maintains only its main diagonal and changes all the other values to 0. So with these definitions, we can enunciate our second theorem that gives us a unique solution for the synchronous firing covariance. So sigma 0 is equals to A transpose times sigma 0 times A. We are removing its main diagonal of this first term and substituting it with this vector of firing variances. And how do we prove it? Well, for the main diagonal elements, it's trivially satisfied. And for sake of notation, since the Markov chain is in a stationary state, I write xit xjt as xi1 xj1. And for the off main diagonal elements, we start by writing sigma 0 by its definition. We rewrite by the definition of covariance. So, sorry. Well, okay. The second line here is the definition of covariance. So we have the expected value of the product of these two random variables minus the product of the expected value of these random variables. Using the law of total expectation, we can rewrite this first term, conditioning it on the previous time step configuration. And here we have the definition of the expected value of the random variable, which we said is equal to the mi and mj. Here we can use the conditional independence of the model. So given the previous time configuration, x, I, and xj are independent, so we can separate its product into two expected values. Here we can rewrite it as the definition we gave. So we have a product of this term here, lambda plus A transpose times x0, taking the ith row of it and the jth row of it. And we also rewrite this term in the right here. Now we can use the linearity of expected value and cancel out some terms and achieve this expression here. Now, considering that AT is a constant, can be taken out of the expected value. So we achieve these sums here. Now, note that both terms have sums over k and j, and we can rewrite all these terms in a single double sum. And note how this term here in the middle is equal to the covariance definition. So we have the expected value of the product of the two random variables and the product of the expected value of each random variable. So we can rewrite it as sigma 0. And finally, we achieve the the term we were expecting. So that concludes our proof and gives us this term here as this expression here, as I said earlier. But we cannot compute sigma 0 from this equation because sigma 0 appears on both sides of the equation, so we cannot compute it. How do we do that? We do that through analytical development in which we vectorize the sigma 0 and achieve this term here, which is a sum from z equals 0 to infinity of L to the power z times the vector of diagonal v. And this matrix here, L, some of its terms are given by the Kronecker product of A transpose with itself. So with this result, we can indeed compute sigma 0. And more than that, we can use sigma 0 and the interaction matrix A to compute sigma 1. So we provided analytical expressions for firing variance, sigma 0 and sigma 1. Now, returning to that example we had before, we already computed the firing mean for each neuron. With that firing mean, we can compute the firing variance of each neuron. With the firing variance, we can compute the sigma 0. So note how the main diagonal is exactly equal to the firing variance vector. And with sigma 0, we can compute sigma 1. There are some important things here to note. As I said before, intuitively, sigma 0 reflects more common neighborhoods. So 3 and 4 have 1 and 2 as common neighbors, and they have a covariance different than 0 here. And sigma 1 reflects more direct connections. So 1 and 3, 1 and 4, we have an edge for 1, 3, 1, 4, and they have a covariance different than 0 here. The first one is symmetric, the second one is not. And note also that the values of sigma 1 of the main diagonal are much larger in magnitude than the ones in sigma 0. Okay, so we did some numerical analysis using these results. The methodology we used was to sample graphs from the stochastic block model with two communities. We have that the probability of inter-community edge is P, and the probability of inter-community edge is Q. So we sample the edge class matrix eta, having value +1 with probability beta and -1 with probability 1 minus beta for each element here. We define the model parameters, so lambda, mean, and meout, and we then compute the statistics on this given network. Okay, so here we have a network with 100 neurons. P is equal to 0.3 and Q is equal to 0.15. Meout is half of mean. Lambda is again 0.25. And note that when we increase the value of beta, we have that this, well, here we have the cumulative distribution function for the firing mean vector. And when beta is increased, this distribution is shifted to the right, which is expected since having more excitatory edges, the neurons will fire more oftenly, so this distribution is shifted to the right. And if we decrease the value of beta, this distribution would be shifted to the left. And having a larger value for me in and me out gives us a wider range, a broader range of values in this distribution, since the contributions will be more, will reflect more differences in the firing probability, and neurons will fire more often or be inhibited more often. Now we have, again, 100 neurons, the same parameters here. Mean here is fixed at 1.23. And I'm here presenting the firing covariance for the pair of neurons. So the y-axis, we have the 100 neurons, the x-axis, again, the 100 neurons. And each point here is the synchronous covariance. In the left is the synchronous covariance for each pair of neurons. And in the right, we have the one-leg covariance. We can clearly see that there is a community separation using covariances. So the first quadrant and the fourth quadrant here are the intra-community edges, pairs, sorry. Red points reflect positive covariance, and blue points reflect inhibitory covariances. And note how there is a difference in scale from synchronous to one-leg covariances. and that the one like covariance is much more reflective of the community structure. Okay, so for our next result, we have a different methodology. We have sampled multiple networks. We used a computer stochastic simulator, which was created for during this master course. And this the simulator generates spike trains. With these spike trains, we compute empirical statistics and compare them with the theoretical result for each of these networks sampled. So here we have 10 networks for each time point. I forgot to say that these spike trains have a length of t, which is the parameter here on the x-axis. And here we plot the absolute error from this empirical statistics to the theoretical results. So for each network, we compute the empirical statistics from the spike trains and the theoretical results. We have an error for that comparison, and we here plot the average and one standard deviation of those errors. So it's important to know that the model parameters have minimal impact on the convergence of the model, and the main factor here is the length of the time series of spike trains from the simulator, both for firing mean and for firing covariance. Okay, so now we can pass to our next session, which is neuronal activity on a random environment. So we're considering that we have the information about the network, but what if we don't have this information? We just know how the network was built. So we are considering that the network is built as a stochastic block model. Again, have two communities and probability edge, intercommunity edge probability P and intercommunity edge probability Q. We consider that the fraction of neurons in each community is alpha 1 and alpha 2. And again, we have the edge class matrix sampled from this term here. We have +1 with probability beta and -1 with probability 1 minus beta. So we gave some mean field approximations for the interaction matrix A. We here separate into two cases. If I is in community 1, we have that the sum of the terms of A transpose, considering that J is also in community 1, is given by this term here, this first term. So 2 times beta minus 1 times alpha 1 times mean times P, which we define as G11, and the other cases are treated in a similar way. And explaining intuitively this expression here, so we have that we have alpha 1 neurons in the same community as I. We have that the average degree of I is P, intercommunity edge is P. We have mean for the contribution weight, and 2 beta minus 1 reflects the difference between excitatory and inhibitory proportions. So these contributions can cancel themselves, and what we are left are the difference between their proportions. We summarize all this information in this matrix G calligraphy here. So it has the terms G11, G12, G21, and G22. And now we provide a lemma that approximates this term here on the left. That is exactly the term we use to compute the firing mean in the fixed environment. So A transpose to the power Z times this vector of 1s, the ith row of this product here, is equal to D to the power Z times this vector 1, 1, times another vector 1, 0 if I is in community 1, times or times 0, 1 if I is in community 2. So here we take the first component if I is in community 2, and the second component if I is in community 2. Sorry, the first component if I is in community 1. And so with this approximation, we can recall our expression for the firing mean. And we achieve only two expressions. One if for the firing mean, one if I is in community 1. So we have this expression here, which we define as N1. And another one for the firing mean of neurons in community 2. So asymptotically, as N increases, we have only two values for the firing mean, which reflects the community membership of each neuron, and that can guide us to recover the communities of our network. But if we consider that we have alpha 1 equals to alpha 2. These two expressions are equal, and we have no information about the community. So M, the phi mean is equal for all the neurons, which we will then call M star. And the phi invariance will obviously be equal as well. G11 is equal to G22 because if we return here, the only difference between G11 and G22 is that here we have alpha 2 and then here we have alpha 1. So if they are equal, both G11 and G22 are also equal. And we write them as G in, and G12, G21 are also equal, and we write them as G out. Okay, so in this special case, we have no information about the communities. How can we do that using the covariance? So to compute the asymptotic covariance, we need this lemma here, which approximates this term we use to compute the covariance in the fixed environment. And again, this approximation here depends solely on the community membership of neurons I and J. So A is the community of neuron I and B is the community of neuron J. And we can recall our equation for the covariance, and we achieve this expression here. So we have only two values for this matrix here, minus G in and plus G out. If I and J are in the same community, then we'll take the main diagonal values, which are equal to minus G in. So we will multiply these fractions here on the left by minus G in. And if I and J are in different communities, we'll multiply them by G out. So again, we have only two expressions that now reflects if I and J are in the same community or not. So even in that special case that phi mean cannot tell us about the community membership of each neuron, we still can know if neurons are within the same community or not using the phi covariance. So we did some numerical analysis using this asymptotic expression and compare them with the theoretical results we had. So what we did here was to sample multiple networks. We computed the theoretical phi mean and covariance for each of these networks and compare them with the asymptotic expressions as n increases. So what we have here is the absolute error between these two ways of calculating the phi mean in an unbalanced case and in a balanced case. That is when the two communities have different sizes and when the two communities have equal size. In the balanced case, we have that both the errors for phi mean of both communities converge to the same point, which is expected since they have the same asymptotic phi mean. And on the left, we have that the absolute error for the community 1 is larger, probably due to the larger magnitude of the phi mean of this community. And so what we did here was to compute the phi mean for all the neurons in the network, compare each of them with the asymptotic expression, and what we present here is the average of these errors and one standard deviation. We did the same for the phi covariance. So again, we have here that one of these curves present a larger absolute error, and this is probably due to the intra-community covariance being larger, which is expected since neurons will have more communications within communities. Okay, so with that, I conclude the results and the explanation of the developments, and I will summarize what we did here. So we built a model for neuronal phi grounded on realistically biological phenomena. We provided exact expressions for both the phi mean and covariance, considering this model we provided. It's something important that we discovered is that synchronous and one-leg covariances give us complementary information, so they should be both used to recover the community structure and the network structure of the brain. And we also saw that asymptotic expressions guide community recovery since they depend solely on the community membership of each neuron, or if neurons are in the same community or not. And with that, I conclude my presentation. I'd like to thank you all for your presence here and your attention. And now I'm open to questions.